I guess I have my answer on if Lee was listening to me.
On my phone and the second.
Oh my God, it's good.
Photons. Okay, continuing. Faisal, put your black hip hop music away, please. No.
He's white, that's Eminem.
Put your white hip hop music away. Wait, is it right to say hip hop can be white?
Yes.
It is? Because wasn't that like a criticism of Eminem's music, that he kind of was, but it was kind of black rap, and he's white, do you know?
It's only because you read a dictionary.
Huh?
It's because you read a dictionary.
I don't know what you're talking about, so I'm just ignoring you. I think we're continuing with a question, wasn't it?
Oh, no.
Okay. Can we look at this one? Yes? Alright. I think you can all do this one. We can do it together. Firstly, frequency. What formula did we use to for Wang and Wang? Listen, please.
Oh no.
Do you care?
Fanula. I'm going to give her name.
Fiona.
Okay, so sorry, Fiona. So Fiona, do you remember the formula for change in wavelength in frequency?
Lambda.
Yeah.
Equal.
Yeah. Anyone remember how to change wavelength into frequency? No.
V equals F lambda.
Yeah, and what's V in this case? Yes, but what is V? The value of V?
Oh, V applies.
C. So C equals F lambda. So what does F equal?
V over.
What's V?
V applied over.
Which is what letter?
V.
So C over lambda. Okay, so calculate that please. Give me the frequency. Thank you. So that is 7.5 times 10 to the 14 hertz. This is part A. Yo, where were you this morning? Even with his UFO alarm going off.
Oh no, I don't hear it.
Okay. And where were you this morning? Alright, we're in the middle of a lesson that we started this morning on photons. Okay, part B. What's the formula for calculating the energy here? You had it earlier today? And H, I think, is on the calculator. So can you calculate this, please? In joules would be great. Sorry, say that again, Yusuf?
4.97.
Yeah.
19.
19, yes. And finally, what is the energy in electron volts? Fiona, the energy in electron volts, how do you convert that?
Divided by E.
Can you do that, please?
P/1 electron volt.
Correct. Are you here for the laptop?
Sorry, I forgot.
I was just commenting with the students that it doesn't matter how old you are, you can still leave stuff behind in class. Who had that laptop?
Mark.
Ah, Mark.
Well, I was the one who brought it up.
Okay, so the responsibility is shared then, is it?
I'm very certification.
Students, anyone see a laptop case around anywhere?
No, I left it, Mark.
He took the case and not the laptop. Yep, sounds about right.
So that's not.
These are all mine here. Yes. Yes.
Right, enjoy.
Okay. All right. Next slide. Yes. Yes. Okay. Right. Here's another quick question to try. Your mobile phone operates at a frequency of 900 megahertz and has a power output of 4 watts. How many photons are coming out of your phone during a phone call per second? So if you think about it, there is a wave that's coming out of your phone. Do you remember, I think we said the frequency is about the same as a kind of a microwave. It's around about there on the spectrum. So that means there's photons coming out of your phone because there's an electromagnetic wave coming out of your phone. And we want to know how many photons come out of your phone per second. Now you can't see this wave. It's an invisible wave. Only light is visible. But there is still a wave that's coming out of the phone. What formulas will you need here? What will you need to do first? First thing you should do is what?
And the watt change the energy.
No.
The power change the power.
No.
to energy.
Before that even.
Megahertz.
Yeah. Oh yes, the megahertz. You don't need to change it because it's already frequency. So it's 900 times 10 to the 6. You multiply that by Planck's constant, and what do you have?
Energy.
You have the energy. And then, what's the formula for power? Work over time. And what's the time in this question? 1 second. So, and the power is 4. Yeah. So, I'll just let you try it, but just before you do, just to note something. Right, look up please. When you use the formula E equals HF, that is for 1 photon. But you have many photons. You actually want to know how many photons you have. So I'll multiply it by n. You're looking for the n. And you know that power equals work over time equals 4 over 1 equals 4. Sorry, my bad. Power equals work over time. 4 equals work over 1. So work should equal 4. So NHF should equal 4. So now you can work out the N. The N is 4 watts divided by the energy per photon. This gives you how many photons you have. It's a bit like saying, if one battery has 1 joule per second, how many batteries do we need? You would need 4, because you do 4 divided by 1. So if one photon has this much energy, how many photons do you need? 4 divided by the energy for 1 photon. You understand this? Yeah? So yeah, you have that there, Yusuf. What did you get? Should be a pretty big number. 31, yeah.
What? No.
No?
No.
Did you include mega?
Yeah.
You did?
Yeah.
Are you sure?
6.7 times 10 to power 24.
Let's see who is right and who is wrong. Now you had a bad track record today, Yusuf. I don't know, Yusuf, this check it out over here. 6.71 times 10 to 24. Okay, continue. Now, have you talked? Yeah, you would have talked about this in chemistry. Listen. Thank you. Now, in chemistry, you talk about electrons. Why did you go to the wrong room when I told you this morning we will use this room?
He wasn't listening to that part.
Were you not listening to me this morning? Yeah, this doesn't look good for you. Either you knew and ignored me, or you weren't listening. Right, in chemistry you learned that metal conductors have a sea of electrons. Electrons are moving around freely in them. On a metal surface you have electrons that are moving around. It is possible to free these electrons if you give them enough energy. This is a bit like ionization. Okay? They require energy to be freed. Therefore, they have a negative potential energy because they're trapped. This energy that is required to free the electron from the metal surface is called the work function. Yes. So, definition, the work function is the minimum energy needed to remove an electron from a solid to a point outside the solid. In other words, to free the electron.
The work needed to free an electron.
The energy needed.
Work is energy.
Work
Energy.
is energy. They're nearly the same, but there's a subtle difference. Energy is just the ability to do work.
Same unit.
Same unit.
This is your last lesson for the day.
Yes, it is. So I think I will sneak out early today.
No.
Of course, I do know I'll need to see people after this class. So by early I mean... No, Yahya got the first slot because...
What to? He was late for your class.
Doesn't matter.
I came.
Doesn't matter. I'm a man of my word. Yahya got the first slot. You'll have to come after him.
What happened to we were one?
Yes, actually. How quickly things can change. Alright, did you write this definition down? Yep, okay. When photons strike a clean metal surface, it will cause the release of electrons from the metal surface. Make sense? If you get enough photons on the metal, you could free one of the electrons. Come on, stuck now. There you go. If and only if the photons provide enough energy. This is known as photoelectric effect. So before you write that down, let me just explain this. No, before you write that, let me just explain. You have a metal surface. The electrons are trapped. If enough energy from the photons hits the metal surface, then... Thank you. Yeah.
Photons.
No, electrons. You were right the first time. Okay. This
What about electrons?
Down to mute. This process of freeing electrons by using photons is called the photoelectric effect. And this was discovered by Einstein. In fact, this is why Einstein won the Nobel Prize for his work on photoelectric effect. Not actually for his work on E equals mc squared, which I think is kind of interesting because that's what people would guess the reason for winning the prize. So the reason I'm telling you this is because I want you to understand how important this effect is. That if you fire photons at a metal surface, you could free electrons. Yes, you need to write this definition down. No, I still have you clicked on mute. I haven't. No, you're still on mute. No, just wait. You're still on mute. Now hang on, I'll turn the volume up. but only a little bit. And a little bit more, I can't hear you. Go on, yeah, what?
Why is it only with metal surface?
I don't think there's a rule that says it has to be a metal surface. I think it's just because the electrons are easier to free from a metal surface, especially a clean, shiny metal surface. I think as soon as you don't have a metal surface and you start introducing things like dirt and roughness onto the surface, then if the electron is freed, so what? It'll just hit a bit of poop on the surface and fall back in. I don't know. Please, no Call of Duty, Metal Gear Solid, or whatever you're simulating there.
So what happens when the electron is free?
Well, what usually happens is, well, two things usually happen. Usually you're freeing the electrons and then send them through a conductor to cause a current. Or often what else happens is the electron is freed from the surface and then you put it into an electric field to fire the electron at something. So basically you can use it to make an electron gun.
But what happens to the metal?
It loses the electron.
So it doesn't like change state?
No, it just loses the electron, which means it becomes slightly more positively charged because it lost an electron. But you wouldn't notice the change in the charge because it's so small compared to the total.
So you take all the electrons out?
No, just the ones on the surface. Yeah. Okay, continue. So here's a very simple photoelectric effect device. You have the metal plate here, and light shines on it, and you produce a current. And you can measure it and all that. So my question is, if you have low frequency and low intensity, what do you think that means? Do you have many photons freed, not many freed? So low frequency and low intensity of light. Low intensity of light means the light is not bright.
The intensity of light plays a major role.
Not bright, dark. You know bright?
It's really
Shiny.
what's this thingy?
What thingy?
The circuit?
It's not so important. Ignore the circuit. I want to know if you have low frequency and low intensity, what do you think that means? Will there be electrons freed? Will there not? Will they be?
If they're low, if they're higher than the threshold frequency, then yes. If no, then no.
Yeah, if it's low frequency and low intensity, maybe you could have some freed electrons. But when they are freed, they'd have a low kinetic
They
energy.
won't fly away.
Yeah. If you have a high frequency and a low intensity, that means you'll have some freed electrons, but they have a high kinetic energy. Now, to help you understand what's going on here, remember we said the frequency of the light is how much energy you have. So what do you think the intensity then represents?
The amount of electrons.
The amount, how many photons of light you have. So what you're saying here is low frequency means low energy light. So if the light has low energy and not many photons, then you shouldn't free any electrons really, and they should not have much kinetic energy when they're freed, because you don't have much energy to begin with. Here, high frequency means high energy photons, and low intensity means not many. So you'll get some freed electrons because you don't have many photons to free them, but when they are freed, they should have a lot of energy because the photon that hit it had a lot of energy. Okay? So maybe you can figure out the next one, yeah?
What's right?
Huh?
What's right?
No. Freed.
Yeah, what's
Freedom, not trapped.
Fredo.
You know?
From
Fredo? What else? Right. Low frequency and high intensity.
Low kinetic energy, but lots of electrons.
Low kinetic energy, but many freed electrons. And finally, high frequency and high intensity.
Many fast.
Many freed electrons of high energy. So these are the four situations you have here. And this is a bit of a surprising result at the time. Okay.
Do lasers count as high intensity?
They could, if they're bright. What's that?
Do we need to draw that?
No, don't draw it, no. You just need the table. Faisal, what's wrong?
Those flies that keep coming
Just
with their
ignore
shape.
them. They're not going to do anything to you.
They're doing tisk.
They're not.
I think you should write a book.
Actually, that's a good idea.
No, it would be terrible.
Now the question is,
Have someone write a book for you.
No, no.
I'm really good at literature, but in Vietnam.
in Vietnamese.
Yeah, in Vietnam.
Okay, I should in Vietnamese. No, because
No, Faisal. She has to write in English. That's part of the charm. And chapter 1 could be starting in Vietnam, and then chapter 2 is moved to DIFC, and then chapter 3 is new friends made, and then chapter 4,
New friend made.
yeah, chapter 4, enemies made. It could be a picture of Wong or something. And then chapter 5 is leaving DIFC, new adventures await.
Stay tuned.
Part 2 of the book.
We continue.
And we need a catchy name for it.
Fun adventures.
Wong's Adventures?
Kung Wong.
For Wong's Fun Adventures. No? For Wong's Adventures in English.
Foreign turbo.
Fong and Turbo. A never-ending friendship.
Love story.
A love story, yes. A girl and her snail. That's the title. That's what we're going for. Okay, did you write that down? Yeah.
Second time.
It was early in the morning. She threw her hair down the bed and then Turbo climbed up her head. It came with its shiny
Shell.
shell.
Yes. Oh, we shouldn't speak of the dead so badly.
Yes.
Bad.
Continue now? Yeah? Yep. Okay. This is the formula here, and let me just explain it, but I think you can work it out. So let's have a look here. We have a metal plate. Before, after. Here is the electron, and here is the photon. In this picture, what is the energy of the photon?
FH.
Or, as I said,
HF.
HF. Now, what is the energy of the electron?
Negative pH. PE.
Your order is totally off today. Negative PE because,
It is trapped.
and the symbol we used is this.
Yes.
Now, afterwards, the photon is gone, the energy was given into the plate, and the electron is released. What energy do we have in this picture? Kinetic energy. So, according to conservation of energy, we have HF minus work function equals KE. Or, as it's more commonly written in the formula book, work function equals, hang on.
KD minus HF. No.
HF equals work function plus
KD.
KE. Okay. So that's really it. That's for this formula. So we can note this, please. Yeah, I say plank, and most people do it, but I don't know if you really should say plonk,
No.
because it's German.
Plank. No, Plank. It's an A, it's not a U.
Let's call them up and ask them. Continue. This is why Einstein won the Nobel Prize.
We don't really care.
Why not?
No one cares about Einstein and Nobel Prize.
Some of you care about Einstein and his Nobel Prize? Thank
Who
you.
is Nobel?
So yeah, with the physics with hands.
Physics what?
I think she made up a new word. Did you say physics science?
Nobel is the physics science.
Yes. Yes. Now, do you care about it?
We need a glossary for her.
Okay. Now, let's try this one now. The work function for copper is 4.7 electron volts. A photon of 250 nanometers hits the metal surface. After the photon hits the metal surface, an electron is freed and travels at a speed of v. Part A, firstly, what is the work function in joules? So how do you get that?
Work function is the
Yeah. How do you get that, guys?
7.53 times 10 to the minus 20.
And how did you get that, Yusuf?
Multiply work function
By E. Good.
What is it a chapter?
No, we're not to that part yet, that's part B. Part B, I want everyone now to try is, using the formula I just gave you, tell me the V, the speed of the electron.
What was the value?
There.
nanometer. What's Planck's constant?
It's on the calculator.
6.234 exponential negative. Okay, what's the constant?
Ask someone with the calculator.
6. Constant 6? Whoa! No,
What is the frequency?
You have to work it out, because I gave you wavelength. Andrew, stop eating your calculator. Did you get an answer? On your calculator. Constant 3.
It's 1.55.
Great, different answers are always good. Yours was, what is it in kilometers per second? 304 kilometers per second. What did you get? Okay, that's close enough. Kilometers per second or meters per second? kilometers per second. Good, good. What did you get? Way off?
Yeah.
What'd you get?
-18.
-18. Yeah. Way off. Alright, let's have a look at it.
Wait.
Faisal!
Not really.
Faisal. We're doing this one now. So the formula is, what did I say? KE equals, what was my formula? HF equals work function plus KE. Now, do we know the H? Yes. Do we know the F? Kind of. We can work it out. Do we know the work function? Yes. This is actually what we're looking for, because it has the V in it. What's the formula for F? C over lambda. So kinetic energy is hc over lambda minus work function. But kinetic energy is a half mv squared. So V is equal to 2 bracket hc over lambda minus work function divided by m square root. Okay, let me put that in on my calculator and see what I get. Well, a constant is Faisal. Do not draw my attention again while I'm doing this question, please. Mass of the electron is constant number 3.
Yes.
Yep. And then in here we have H. Is that Omar? What constant did you say H was? 6. And what constant is C actually? C0, I think it is on the calculator. We might as well get it exact. It's like in the 30s, is it? Or 20? What is it? Yeah, that's the one. What's the wavelength?
250 nanometers.
And then finally, I need the work function, which is 7.5 times 10 to the power of minus 19. Very good, very good. 312.8 kilometers per second. So it's going pretty fast. Okay. Next. The work function means the electron has this energy in order to free it. If a photon has exactly this energy, then the electron is just about freed, but it doesn't have any kinetic energy. That is, if E equals HF, then the F is called the threshold frequency. In other words, it's the minimum frequency required to free the electron. So, let me just write that down here. HF equals phi plus KE. But if you don't want any kinetic energy, then you have this formula, which means F0, this is the frequency you need to free it, but nothing else. What I mean is just the energy to free it. And this is called the threshold frequency. Can you make note of the last sentence here? This part, F0.
The energy required or the frequency required?
The frequency required to give it the minimum energy required to free it.
What's the photon?
The what?
To give the electron.
To give the photon, to give the electron, yeah. Yeah. Andrew, Would you not let Lee lie on your shoulder there? Look how tired he is. He can barely keep his head up. John, just like stick your shoulder out right. Yeah, exactly, yeah. Yes, put a blanket over him. Yes, yes. Sorry, Lee, we were worried about you, so I asked Andrew to put a blanket on you. You looked cold. Are you okay? You go back to sleep. It's okay. We're just doing physics. Okay. Continue. You have this? I think this is the last example. Yeah. The work function for gold is 1.5 electron volts. What is the threshold frequency? Calculate, please.
So we won't be moving at like a threshold frequency.
The electron is freed but doesn't really go anywhere.
Does it become the velocity?
Correct. What's the answer here?
1.23
Hertz then, yeah. Okay, we'll just do the part A here. Okay, we'll start the next lesson. These are the questions to try for this lesson, and we'll do the final lesson now.